Hey, welcome. Have you ever really thought about the objects all around you? I mean, why is it that some things can stretch and then snap right back, but other things bend and just stay that way? Well, today, we're going to dive deep into the physics of why things stretch, bend, and sometimes even break.
Yeah, it really all boils down to this simple, everyday question. A rubber band snaps back into shape, no problem. But a paper clip, once you bend it too far, it's changed for good. The answer to this little mystery lies in two fundamental and kind of opposite properties of materials: elasticity and plasticity. And here's the roadmap for how we're going to unpack all of this. We'll kick things off with the basics: elastic versus plastic. Then we'll get into the language physicists use to talk about this stuff: stress and strain. After that, we'll uncover the simple rule that governs it all, learn how we measure it, and finally, we'll put everything into action.
Okay, let's get right into it. Section 1. Elastic versus plastic. This is really the science of bouncing back, or, not bouncing back.
So first up is elasticity. Think about that rubber band. This is its superpower. You apply a force, you stretch it out, but the second you let go, bam, it zips right back to its original shape. That incredible ability to bounce back is what we call elasticity.
And on the flip side, we've got plasticity. This is our bent paper clip. You apply a force, and the object permanently changes its shape. It doesn't spring back. It's kind of like sculpting with clay, right? The change you make is supposed to stick.
So let's just lock this in. Elastic materials like quartz, which is almost perfectly elastic, always return to their original shape. Plastic materials like wet clay or even paraffin wax deform permanently. That change is absolutely there to stay. Now, to really understand what's happening inside these materials, we need to learn the language of physics. And when we talk about deforming objects, that language is built on two absolutely key ideas: stress and strain.
Let's start with stress. And no, it's not just that feeling you get before a big exam. In physics, stress is a super precise measurement of the internal forces at play inside a material. It's all about how much force is applied over a specific area. You pack more force into a smaller area, you get a higher stress.
This little diagram here shows us the most common kind, which is called normal stress. Just imagine you're pulling on both ends of a wire. That pulling force is acting perpendicular to the wire's cross-section, and that force, spread out over that area, is the stress. Okay, so if stress is the cause, then strain is the effect. Strain is simply the measure of how much the object actually deforms or changes shape. But what's really crucial here is that it's a ratio. It's not just about how much it's stretched, but how much it's stretched relative to its original size. And this is a perfect example of what we call longitudinal strain. Think about it. A 1 centimeter stretch is a massive deal for a tiny 10 centimeter wire, right? But for a 10-meter cable, you'd barely even notice it. Strain is what captures that all-important relative change. So we've got stress, which is the force, and we've got strain, the deformation that happens because of it. But how are they connected? Well, it turns out that for a huge range of materials, they follow this incredibly simple and elegant rule. But first, we need to talk about a critical idea: the elastic limit. This is the point of no return. As long as you stay within this limit, your object is elastic. It'll bounce back. But if you go beyond it, you've entered the world of permanent plastic deformation. That's the bent paperclip zone. And that brings us to the main event, Hooke's law. And it is beautifully simple. As long as you are within that elastic limit, stress is directly proportional to strain. That's it. In other words, the more stress you apply, the more strain you get, and it happens in a perfectly predictable way. You double the stress, you're going to double the strain. This graph from the source material just makes Hooke's law crystal clear. You can see the elongation, that's the strain, on the bottom axis, and the load, which is our stress, on the vertical axis. That perfectly straight diagonal line, that shows a direct proportional relationship. That's Hooke's law, right there in a picture. Okay, so this proportional thing is fantastic, but we all know that different materials stretch, well, differently. A steel cable is way harder to stretch than a rubber band. So how do we put an actual number on that stiffness? We use something called a modulus, and for stretching or compressing, we specifically use what's called Young's modulus. It's simply the ratio of stress to strain. A material with a high Young's modulus, like steel, means you need a ton of stress to get just a tiny bit of strain. In other words, it's super stiff. And it turns out there's actually a modulus for every type of deformation you can think of. Young's modulus is for changes in length. Then there's bulk modulus for changes in volume, like squishing something deep underwater. And shear modulus is for changes in shape, like if you push the top of a Jell-O mold sideways.
All right, theory is great and all, but let's see how this all comes together to do something practical. Let's use everything we've just learned to solve a real-world physics problem taken straight from our source material.
So here's our setup. We've got a wire, we know its length, its area, and what it's made of, which is how we know it's Young's modulus. Now, we're going to hang a 15-kilogram mass on it. The big question is, precisely how much is that wire going to stretch? To figure this out, we just have to go back to our definition of Young's modulus. Remember, it's the ratio of stress, which is force over area, to strain, which is the extension over the original length. All we need to do is rearrange this formula a little bit to solve for the one thing we don't know, the extension. Okay, let's just follow the calculation right here in the source notes. You can see first the formula is rearranged to solve for E, which is our extension. Then the force is calculated from the mass, and after that, all the known values are just plugged right in. And after all the number crunching, we get our answer. That 2.5-meter wire stretches by this incredibly tiny amount, just under 0.2 millimeters. Now, it's a small change, for sure, but the key takeaway is that because of the physics of elasticity, it is a perfectly predictable one.
And really, that's the power of understanding these principles. From the massive steel cables holding up a bridge to the delicate strings on a guitar, the predictable nature of elasticity is absolutely everywhere. So my question for you is, where will you see it at work today? Thanks for joining me.
Thank you for watching my video. Please like, subscribe, and hit the bell icon.